Hi friends, so welcome back to the course. So today, if you're wondering just why it is a lot of physics, we haven't seen the differential equation yet, or the partial differential equation yet. Don't worry, stay calm because I believe setting up the basics and the fundamentals right will help you a lot in appreciating the whole setup in a much better way. So, one last bit of information before we start deriving the equation. The concept of specific heat. You would have learned this in your high school physics. Specific heat. It is called, it is usually denoted as Cp, but here I will go with the notation of sigma. So, what is specific heat? Specific heat is the amount of heat that you have to supply uh, to a material of, let's say, 1 kg. This is the amount of heat that you have to supply to get a rise in its temperature by 1 degree Celsius or 1 Kelvin. So this is the definition. So put it in mathematically. So if you supply, let's say, Q amount of heat, Q, the unit of Q being joules, to an object, let's say this is our object of mass m, then it will result, or this will increase the temperature of the particular object by delta T. Okay, so if you have a object of very high specific heat, then you need to put in more amount of heat to get the same temperature rise. If you are comparing two objects, I hope you all would have learned why water is used in the radiator for automobiles. This is one reason. Water have a very high specific heat, specific heat capacity, because I think it is nearly 4,200 4,200. So this is pretty high for water. Let's leave that apart. So physically, Cp, specific heat capacity, represents the capability of an object or a particular object to store thermal energy or heat energy. Okay, so that is good, I guess. Now let's move forward and start deriving the heat equation. Okay, so we have clearly understood what is heat flux. Then I just now explained what is specific heat capacity also. So now let's see, let's look at this portion. So here what I have done, I have just isolated a small portion of this particular bar. I have just cut a piece, like let's say I have cut a piece and removed it apart. So this is that portion of the which I removed from that bar which I have shown in the first slide. So, this length is very small. This is of length dx. So we do this whenever we derive all these major equations. So, and this is the cross-sectional area, so I assume the cross-sectional area to be remaining constant, and throughout this length dx it is ax. So as I told you in the previous lecture, now I'm going to apply a basic physical principle, which is the conservation of energy. It's pretty simple. I'm telling the rate of change in energy will be the difference of the energy that comes in minus the energy that goes out. So it's pretty much like you have a can, or you have a bottle or a can, whatever you can take. Let's say you're supplying water at the rate of, let's say, 3 liters per second, and you're taking out 2 liters per second simultaneously. Then the rate at which the volume will be increasing in this particular container will be How much? Pause the video for a while and guess. It will be 1 liters per second. Okay, so similar concept, the same concept can be applied here. So put it in mathematical terms. um, okay, just before that, just try to understand what is coming in. So this is the heat flux that is coming in. So the rate at which energy is coming is qx times, I will write ax, because this is, let's say I will make it watts because this unit is watts per meter square, and multiplying with meter square makes this whole quantity in watts. Similarly, by Taylor series expansion, if you are not sure what is Taylor series expansion, please go or read any particular article that you get on an internet, or you read textbooks. Taylor series helps us to predict the value of a function at a slightly, let's say you know the value of a function at x, then Taylor series help us to predict what is the value at f of x plus dx. So the same concept applied here. You want to know the heat flux at this particular point. Then the heat flux at this particular point can be expressed like this. Similar argument which I applied here. This is the unit will be in watts per meter square. So multiplying it with the cross-sectional area, this particular cross-sectional area gives me what is the energy that is going out. So this is the energy that comes into the system, and this is the energy that goes out of the system. Okay, clear? Now what the rate at which the energy is getting stored will be, so this is the density, this is the volume, so this will give you the mass, rho is the density and ADX is the volume, so this will give you the mass, and Cp or the gamma, which is the specific heat capacity. So this will tell you the rate at which energy is heat energy or thermal energy is getting stored in this particular object. Now, by common sense, this should hold true, right? So now if we plug in all these equations back here, then what we will get is, let's write it, qx ax minus qx ax plus dou qx by dou x into dx into ax will be rho Cp dou T by delta T times A into dx. Apologies for using T again. I told you in the previous lecture we will be using U only, but both of these things are same. T is pretty much equivalent to U. I am using these notations interchangeably. So let's say now these two terms is going off. Now what we are left with, dou qx dou x dx will be rho Cp dou T by T. Clear? All others just vanishes or cancels out. Now if I know from my Fourier's law qx is minus k dou T by dou x, so if I plug it in here, then it will be k times dou square dou T by dou square is equal to rho Cp dou T by T. Okay, that's it. Now let's see, here you have a partial differential equation. So once again, we were not looking we just applied some simple physical phenomena or physical principles to this equation. Finally, let's see what we are left with. We have a partial differential equation in our hands right now.